I'll be giving you an overview about binary search, some examples, and how you can tell if binary search can be used for a problem. So first, what is binary search? Normally, if you have a list like this, and you want to search for an element, you can just loop through all of these different elements one by one and see if the element is in the list. You can also return in the index if you feel like it, or just if the element is there in the list. Now, this has a complexity of O of n time, which is pretty good, but can we do better? If we look at this list, you can notice that it's actually sorted. It does have duplicates, but it is all sorted. So can we use any extra information to speed up our process? Yes. And this is where binary search comes in. With binary search, every time we look at an element in the middle of the list, we can see if it's greater or less than our target value. Let's say we're trying to find if the number 8 is in this list. In this case, 6 is actually less than 8. And because this is a sorted list, we can narrow down our search area to this half of the list, because we know anything to the left of 6 is not valid, and 8 is greater than 6, so it has to be to the right of that. Then we look in the middle of this portion, which is 10, and we notice, 8 is actually less than 10. So then we can further divide it into these two, which then if you calculate the middle to 7, it's greater. Okay, then we narrow it down to 1, which is 8. And we see, actually 8 is our target number, and we can return true, which is obviously the answer. But let's say our target value was actually 9. Then we'd go through all of the same thing, except here, we'd notice, 8 is not 9, and now our search area is narrowed only down to 1. So this means that it is not in our list. So if we put this into code, basically what will happen is you have a left pointer, which will go to the beginning of the list, a right pointer, which goes to the end of the list, or the size of the array -1, and then you have the middle, which is just in the middle of L and R. And the way to calculate this properly is to do L plus R minus L divided by 2. We do it like this to make sure that we don't have any overflowing if R and L are very large. Then we have a while loop, which is while L is less than or equal to R. In this case, we have less than or equal to, because we don't want to have something where our left pointer, which is left and right, marks our range. We don't want something where our left is to the right of our right pointer, right? Because that would mess up our whole range. So we need to make sure it's between it. And we also need to search everything. So we have to make sure that even if L is equal to R, we still check that value. Then we recalculate M, which is the same way we did here. And then we check if M is less than our target value. If it is less than our target value, then we make L equal to M plus 1, because again, we want to push our target range outside. And then else, which means that and then else if m is equal to t, then we'll actually return true because, we found our target value. And then otherwise, which means that m is greater than t, we just make r equal to m minus 1. And obviously this depends for the exact implementation, but you can change the orientation, and normally in binary search it goes like this. Okay, so now let's look at one more example. Here we have a bunch of falses followed by a bunch of trues, and we need to find out where the first true is. So in this case, we can also just iterate through all of them until we hit the first true. This would be O of n. But again, we can actually use binary search here. So let me show you how to do that. If we look at the middle, which is this f, we know that in this case, since this is f, everything to the left of it are also falses, so there's no point looking there. And so the trues must be after it. So we can narrow down our search area to all of this. Then we see that our middle is this true. And we see, okay, great, it's true. There's no point looking after that because they're later than t. And so the only place we want to go is before, because we want to find the first. So then our search area just narrows to this, and we see, okay, it's true. So then we just return this place. The code for this has a very, very similar control flow to what we have over here, except instead of doing m equal to this plus 1, we have to make sure that we include t, because, for example, if this was an f over here, we still need to keep this in our search area because it still might be the answer. Now, how can I identify if a given problem can use binary search? Well, all that it has to have is there must be some definitive order to it, which you either get it ordered as an input or you can order it somehow. In this case, it was sorted, but in this case, you know that there's a bunch of F's first and then some trues. Then you just have to make sure that if you look in the middle, you can devise some information about which half to continually search into. If you take all of these into account, you can write your very own binary search program. And all binary searches follow this similar template, but can be changed depending on the problem. In the description below, I have kept a couple extra problems from Leetcode, and if you want to try a bit advanced binary search problems, you can consult those and try them out. Thank you for watching. Please subscribe and like the video if you enjoyed, and I'll see you next time.